All right, thanks for joining me this afternoon. I'll try to keep it brief. We're going to talk about static single assignment, a normal form, and a little bit of continuation passing style. So static single assignment is a very pervasive methodology for designing intermediate representations. It's used in all sorts of different compilers. And it's used in different compilers because it disambiguates data flow reasoning. It makes the code easier to understand if you're looking at a variable, where was the proximate point at which it was defined? So if I look at this piece of code right here, I can see I've got these variables x and y, but throughout the execution of the code, x's value is going to change. And so if I looked at this x right here, I can see if I look at the code that its proximate definition was right here. But maybe, for example, if I was thinking about this version of x, well, that would have been clobbered, right? So in SSA, that's made explicit. So here I've got x sub 0 and I've got x sub 1. Every time I write to the variable, I'm going to introduce a fresh binding. And then from the rest of the code, that binding is going to be the one that's going to be used. It's not going to be x, it's going to be x sub 1, right? So down here, when I use x, I'm referring to this x sub 1 binding. And here when I use y, I got y0. Here I use x2 because it's been reassigned. So if a variable is written multiple times, I'm going to replace it by multiple unique instances. And then I'm always going to refer to the one that's currently live at the current point. So who cares about SSA? Well, there's a bunch of reasons, but in general, SSA is going to make it obvious what version of a variable is currently live, right? In the case when there's variables that are being assigned throughout the program or throughout the function, throughout the basic block, we really want to know when we look at a usage of a variable, what was the proximate point at which it was defined, right? There's a bunch of reasons we're going to want to know that. One is going to be things like data flow analysis. Another one is going to be when we do register allocation, we're going to want to know what's alive at the same time, because everything that's alive at the same time kind of puts a lower bound on what we need to keep in registers, ideally. We might have to spill, of course. So, for example, another reason we might care is that, well, really, the IR is kind of already a little bit in an SSA-like form. And here's what I mean by that. If you have a variable stuffed in a register, well, in x86, it's pretty common that machine instructions will use source registers as their destination. And so, for example, this add rbx r8 instruction will clobber whatever was in r8. So if r8 was carrying a variable, well, now that's been overwritten because now it's the result of r8 is equal to r8 plus rbx. And so there's a bunch of benefits to SSA, but we always have one unique definition of a variable. And whenever we see a variable, it's easy to go scan through and look in the program or index and find out where was that proximate definition site. And it's also easy to take things like SSA variables, because now it's very clear where they've been defined, and then to go translate them back into registers or stack locations, for example. Now, a related topic that we see in functional programming and functional compilers is something called a normal form. So a normal form is kind of a functional equivalent of SSA. They're not really different. You can see it just as sort of two ways of viewing SSA. And in ANF, we have simple and complex expressions. Atomic or simple expressions are those which can be evaluated in a bounded number of steps. So this is variables. You just look them up in the environment, right? Immediate values or constants, things like literals, strings, stuff like that. And then complex expressions are things that are performing computations, calling a function, combining results, adding two things together, for example, or doing conditional control flow branching or something like that. Now, in ANF, we have a rule, which is that every complex expression involves only simple arguments. So for example, if I look at this piece of code down here, I've got plus of plus x, y minus z. And then I've got plus of x and quantity minus x. So if I were to write that in ANF, I would have to use this equivalent form. Basically, what I have to do is I have to introduce these administrative bindings. At one point, I thought ANF was called administrative normal form, which I think many people call it that, but I've heard that maybe that's not really the official name. I'm not really sure. But in any case, we introduce these administrative bindings. So here I introduce this, see how I can't do this quantity plus this quantity because both of these are complex, so I need to make them simple. Now, in this case, this little thing that I've got highlighted would be fine if it was just that, because the arguments y and y are both simple. And so I lift that over into intermediate 0, make that plus y. And now, same thing over here for intermediate 1. And now I can define x using the result of adding both of these, because now these things are both simple, right? And now I can introduce this new intermediate binding for 3, int 3. And now my result is just going to be x plus the result of int 3. Okay, so a little exercise here, convert this to ANF. I'll just show the answer. All right, so you can work that one on your own time if you want. And ANF is kind of SSA, right? So if we think after the uniqueify pass in our compiler, ANF will introduce a bunch of administrative bindings that will have GenSimmed names. After the uniqueify pass, any place where there were two distinct bindings for the same variable x, uniqueify will have made them distinct. So the fact that we've got uniqueify plus the fact that ANF only introduces unused fresh variables, that combination is going to give us this SSA-like form. And in LVAR or R1, all of our expressions after we run the A normalizer, the ANF pass, are just going to be linear chains of lets, where the right-hand side of a let is always going to be sort of a complex expression where you've got atomic arguments. And in SSA, we generally have this notion of a basic block. The idea is that in SSA, we've got these sort of chains of definitions of variables where we've only got these simple arguments on the left-hand side. And control flow starts at the top and ends at the bottom. And every variable has a unique definition over here. So that's what we see when we look at our ANF over here on the left. We can see that really it's just, there's indentation because we put the let here, but really we can think of it as being a linear chain of events that are going to happen where we're going to return the thing that it computes to in the end, right here. So we're only seeing some aspects of SSA right now. SSA also involves branching control flow, and we're going to talk about that soon. So in this lecture, I'm discussing SSA as viewed through the lens of the current project, but very soon in the next lecture, we're going to start talking about branching control flow, and then SSA will have some other features. A big thing that I'm trying to do is relate the sort of functional compiler's perspective and imperative compiler's perspective, and that's going to be kind of easy because we're going to start by building essentially imperative compilers for very small languages. But we're doing it in a functional style. So the next idea I want to talk about is continuation passing style. This is an idea that comes from functional programming. So a continuation is a function that represents the rest of the computation. And there's a lot of different styles of continuations. There are continuations that are baked into the language. These are essentially control constructs, like more powerful exceptions. And call_CC is an example of this. If you've ever programmed in a Scheme or a Lisp-like language that has continuations built in as first-class items. Now, in those languages, you can always grab the continuation. That's actually not the case. If you're programming in C, C++, Java, you generally can't just take control of the continuation other than maybe to like manipulate the stack via the stack pointer manually, which you could always do if you go and off into assembly or something. But there's also a notion of continuations that you could do without call_CC. So it's not like, when I was learning this stuff, I got very confused about there's the call_CC continuations, but then you could also just write continuations manually by programming in CPS in a manual style where you don't use call_CC. There's also the ability for the compiler itself to expose to use continuations internally, basically to use CPS as sort of an internal convention, but not expose that to the user in the sense that you don't give them exposed access to be able to invoke continuations. There's more complex topics like delimited continuations and other things like that. And also exceptions, which are similar to continuations and related, but not quite as powerful. And it's important to kind of distinguish all these topics. So I'm going to start off by talking about manual CPS. So we can manually write in CPS by sort of following a calling convention. So what I'm saying is basically, if you don't have continuations baked into your language, so Racket does, but like even if you were programming in a language without continuations baked into the language, like maybe like C, for example, if you were willing to use function pointers or something like that. Or I guess in this case, it needs to be a language probably with closures, but even if you're not using call CC, you can write manually and get the benefits of CPS by following this calling convention. And the idea is that every function accepts an extra argument, which is continuation. We're going to call that K. In this case, it's going to be the last argument, but it just has to be some canonical argument, maybe the first, the last, something like that. And every computation returns its result by invoking its continuation. So here, notice that we sort of evaluate to X by just returning X. We're the last thing in foo, and so naturally we evaluate to X. But we're going to say in this manual CPS notion that no, that's wrong. In fact, what you have to do, you have to be pedantic. You have to invoke the continuation. And of course, if you take this style, then it becomes a real pain, because literally everything has to be a call to continuation. Every little individual single step in the program, even things like calling plus and calling times, the built-ins, and even the idea of, well, maybe we're going to say let's okay. We'll talk about that in a second. But every little thing is going to need a continuation. And so to translate a block like this, well, first I want to read X. So I might invoke this function read K, but now I have to call read K with a continuation if I'm going to be pedantic about it. And again, this is just to show how we could do it if we were trying to be fully precise and manual about writing our CPS. What I could do is I could say all of the built-in functions have a continuation version. So I've written a version of them down. And also at the very outer level of the code, this whole thing here is going to evaluate some value. And then what's going to happen with that value? Well, the observation is that really at the outer end of the code, there's some outer continuation that's sitting and waiting to like print the result to the user, maybe like displayLin. So here I've called that top level return. So now let's see what happens. Well, I'm going to invoke read, and I need to call it with a continuation. This is going to be that continuation right here. And I'm going to say when you're done with read, invoke this continuation that binds read result. And then I'm going to let X be read result. We're going to talk about let in a second. It's a kind of a CPS already. Then within this body, well, I can't call plus because first I've got to call times. So I'm going to multiply X by 2, and I'm going to use this version of times that's going to accept a continuation that's going to bind mul result. And then what I'm going to do is I'm going to add whatever that result was to 3, and then I need to pass this a continuation as well. In this case, it's going to be top level return. And that's the original return that gets us out of the entire expression. And that's going to display lin. Now, what about this let? Well, I can see let as kind of a left lambda, meaning I can view let, in this case, in CPS, as basically say, first execute the body, and then as you're executing the body, pass the continuation that binds the result of the body, X, and then, first evaluate the thing you're binding X to, not the body. First evaluate E, and then as you're evaluating E, pass the continuation that binds X, this variable we want here, to be in scope of the body so that when we evaluate the body, we execute it. But then, of course, remember, this is a little bit imprecise because we've got some outer continuation that we need to be passing on to EB here. So, but in our case of R0 or, R1 L of R, what we're doing in project 2 of our class now, we can view these long chains of lets with simple arguments as basically being in CPS. So instead of explicit continuation being passed to something like plus or times, we don't generally want to do that, right? We're just going to say that the continuation of these simple functions right here is just going to be the body of the let. Now, of course, in real assembly, primitive functions do not accept continuations as arguments, right? So things like the add instruction or the minus instruction, it's not like you've got an add and then jump instruction. That's not really how it works, right? It's just that the add instruction implicitly continues on to the next instruction. So when we linearize and flatten these things into a basic block, there's going to be an implicit notion of control flow that's going to be by virtue of the fact that you're linearized into a little block and you're sitting out of it. And then we're going to have explicit instructions that jump out of blocks. Those are going to be the end of a block. So we'll talk more about that soon. Now, just to show you kind of how you could manually program in CPS a little bit, I don't actually think it's a good idea to be manually coding stuff up in CPS, even though it feels like kind of a cool thing to learn. CPS is basically programming with GoTo, and right, GoTo is to be discouraged. We generally don't want our code to be messy. But I think it's reasonable to show a worked motivating example here. So one that I'd show is recursive tree traversal. So I've got a little racket type predicate here that characterizes a tree. It's either empty or it's a node with two trees as arguments. And now it's easy to write a tail recursive version of binary search, assuming that the tree is sorted. All we have to do is, if we hit empty, we know we didn't find the element, so it's false. Otherwise, what we do is we check to see if we found it, and then we check to see if we go left or right. Now notice these are both tail calls, right? They're in tail position. The result of this binary search is this binary search here. And so these are both tail calls. They don't push any stack frames. But it's a lot harder to imagine how we could sum up all the elements of a tree. The reason is that we basically need to do backtracking. And so what I'm going to do is I'm going to add on this extra continuation argument. The continuation K is going to say this. It's going to say, when you're done processing whatever you're doing, invoke K, and here's the rest. Now, when we initially call some tree on the top of the tree, the whole tree, we're going to have to pass some continuation, right? In the same way as when we write sort of a tail recursive accumulator function, we have to pass an initial accumulator. So what should that initial K be? Well, it's going to be the identity function, it turns out. So to call some tree, well, how do we implement it? Well, first, when it's empty, the deal is, remember this, we always have to return our result to our continuation. So we can't just return 0. We need to invoke K with 0. When we've got a node, what are we going to do? Well, first, we're going to call some even tree. Ooh, no, this should just be some tree. I copied these over from some notes. This should be some tree on T0. And then we need to pass some tree a continuation. So some tree is going to get this continuation that's going to be a lambda, and its argument is going to be T0 sum. The body of this lambda is going to call some tree again on T1. We're going to pass it a continuation, which is T1 sum, and now we're going to invoke K on the result of plus T0 sum, T1 sum, and V. And now notice here, I'm not invoking this weird form of plus where I pass a continuation. I'm just calling it in direct style, right? And that's pretty common. Even when I write in manual CPS, I don't want to literally write everything with a continuation, right? I just kind of want to call this as a direct call. It's going to return very immediately, and then I'll call K on that. So just to conclude, I have another video on how to convert into ANF and CPS. The basic idea is we're going to write a function, CE, which can take the continuation as its argument. The continuation is going to accept an atom as its argument, and then the algorithm is going to generate administrative bindings to kind of linearize and flatten the control flow. Now, what I show here is actually a CPS conversion algorithm. I'm going to discuss the optimization later in class that's going to generate fewer administrative bindings. I'll just hover over it here, but like I said, I have a longer video on this. The basic idea is that when you get to plus, you're going to generate you're going to use gensim to generate a new symbol that has never been seen before. That's what gensim does. Then you're going to call convert expression on E0. You're going to pass it a lambda that's waiting to accept some syntax representing the result of converting E0. You then call, again, once you get that result for E0, you're not done because you need to now convert E1 and bind a result which is syntax representing E1. And now the whole return value is going to be this administrative let binding, which is going to define this new variable. So you're emitting a new let here. that's going to define this new variable. Now you know by virtue of the way that you've set this up that A0 and A1 are both going to be atomic values. They're either going to be variables, symbols, or they're going to be integers. And so when you do this plus here, you know that both A0 and A1 will be atoms. And so this is going to be good, but now you need to call K because you're waiting to be called with the result. Your continuation K needs some atom. And in this case, that's going to be this fresh variable you just generated here, E0 res. Okay, so if you want to see more of how that works, I've got another video on it. But otherwise, thanks for tuning in today. Have a good rest of your day.